Thank you very much, Andrew, and thanks for having me here. Yeah, the official title is Hilbert 10 by additive combinatorics, and the first part of the title appears right away. So the story starts beginning of last century, and this was the second ICM in Paris, where Hilbert wrote a list of 23 problems that were fairly influential and throughout the last century. And today we focus on problem number 10 problem of this list. And I will use this notation H10 over Z. So Hilbert 10 over Z, and the reason is that we will soon replace Z with other rings and discuss the same question for different rings. And the question as formulated by Hilbert back then was, is there a mechanical procedure? So it was an unprecisely formulated question, as several of these 23 problems, they were broad problems that decides solvability of all Diophantine equations. So let me make it slightly more precise. So you can turn this mechanical procedure in Turing machine, which Turing did after this. So it's so is there an algorithm essentially that takes as input, decides takes as input a polynomial, any polynomial p in any number of variable p1, tn, and outputs outputs yes if there is a z point and no if there is no z point. So it's able to decide yes if you can find a vector a1 a in z to the n such that p of the vector is 0, a1 and 0, and no otherwise. So these are called Diophantine equations for those of you that don't do number theory because of oh, sorry, maybe I should have used, okay, I'll use the board. Diophantus of Alexandria, I think 3rd century before Christ, studied already these kind of questions. He has a book about several specific equations, and in number theory we study many such examples. And if you have never seen this, maybe here is an example. Here are a few examples. If you consider the first nonlinear example, perhaps is the Pythagoras triples, where you have a completely parameterized set of solutions that look like this. And C is 2 times Mn. And the set of solutions, this is the entire set of solutions. So it's an infinite set, even up to scaling, and it's completely understood. And in contrast, you can already think what happens in higher degree, and you have equations of this form: y squared z to the d minus 2 equal p of x z, where this is homogeneous of degree d in zx in zxz, and is non-singular, meaning it has no repeated roots. So this is an homogeneous equation of degree d, and here there is already a dichotomy that if d is at least 5, you have finitely many solutions up to scaling. Solutions to scaling. You can always scale a solution because it's homogeneous. And this is a deep theorem of Faltings, special case. And the case D is 3 or 4. It's an edge case which lives between this parameterized world and the world of finiteness. And it's object that will come later in the talk. Those are so-called elliptic curves. And the set of points of these elliptic curves form a natural and abelian group. And we will say more about this abelian group in a bit. So this is an example only in dimension 1 up to scaling. These define one-dimensional objects of Diophantine equations. And the situation is already very complicated. This is a theorem from the 80s, I think. Falting's won a Fields Medal for this. And even knowing the finiteness, we don't have an effective procedure to determine the set. So if you don't assume conjectures, actually, for instance, at the moment, we don't know the answer to this question if you restrict to one-dimensional objects, so to equations in a small number of variables. All right, so this is, yeah, even in the simplest case, you run immediately into difficulties. And Hilbert question from this perspective is a very ambitious question, is asking whether you can, this problem that looks already quite complicated at this stage, as a completely mechanical resolution. So let me give you right away the theorem from the 70, from literally 1970. That's a strange alphabetical order. Matiyasevich, Robinson, Davis, and Putnam. And the answer to this question, so there should be the mark somewhere, is no. So theorem says that people phrase this theorem by saying that H10 over Z is undecidable. In other words, there is no such theorem machine. There is no procedure that as an input can take a polynomial in any number of variables and over Z and decides whether there is a Z point. All right, so the focus of today's talk maybe comes from the motivation, from the historical motivation of the question. It's speculated that Hilbert was an optimist, and he was expecting that actually the answer was yes, was going to be yes. So if you have a positive answer over Z, then it's not hard to see you have a positive answer also over the rational numbers, and the other direction is not true. You might, and at the moment we don't know what's the status of that. We know that the answer is negative over the rational and over the integers, but over the rationals, it is wildly open. We don't know whether the answer is speculated that the answer is negative, but I will come back maybe to that later. But there is no line of attack that is plausibly considered promising at the moment. So if you have a negative answer, enlarging the ring makes you lose the answer, because maybe if you enlarge, for instance, if you enlarge Z to C, the answer is always yes. So there's always a C point, or even to Q bar, or even to Z bar. It's a result of Rumley that over Z bar, the algorithm that answers always yes is a good algorithm. So it's an interesting question once you know that the answer is no, to enlarge the set of possible rings. So the class of rings today is, we will focus on finitely generated infinite Z algebras. Let me make this precise. So everything is commutative. All rings I will consider today are commutative. And so this means that your ring R will literally be formed by a finite set of elements A1, AN inside the ring. And then you take polynomials with integer coefficients, and you get the whole ring. So every element of the ring can be obtained by adding and multiplying finitely many variables. Maybe there are relations between these variables. Maybe I'm not saying this is equal to a polynomial ring. This is a subset, so it could be maybe that A square is equal to AJ or other relations like this. So it's any polynomial ring modulo any ideal of the polynomial ring. That's what I mean by finitely generated. And why infinite? Because if you take a finite ring, then there is an easy algorithm to test solvability. You can just run over all elements and check whether you ever get zero, and that's a valid algorithm, and the question is not so interesting. So yes, so let me explain now that we have a theorem, we have sort of the goal. Let me explain a little bit what were the main ideas behind this theorem. I will also say a little bit about the funny alphabetic order. Yeah, please interrupt me for any questions. So let me say something about the strategy of the proof. And to say that, I want to give an elementary definition that will be important throughout the talk. If you have a ring R as there, and you have a subset of R to the n, where n is a positive integer, this is said to be Diophantine if it is the projection of the zero set of a polynomial, it may be more than n variables. So formally, if there exists a polynomial in m variables, where m is at least n, such that the zero set of the polynomial, if you project it on the first n coordinates, and you take the zero set of the polynomial, you get S. So this is zero set. Let me not spell it out. So these are the set of vectors in over R. So these are the set of vectors in R to the m that vanish under the polynomial. You project it. This is projection in the first n entries. And yeah, so you can view a polynomial in m variables as an algebraic family of polynomials in m minus n variables, where the first n variables you think as a specialization. And saying that it's Diophantine more intuitively saying that it's the set of specialization such that the resulting polynomial has a zero. So that's what is a Diophantine set. And here are two not too trivial examples of Diophantine over in case R is Z. You can take, this is maybe the standard example people always give, the non-negative integers, and they're defined by the so-called four-square theorem of Lagrange. This is a Diophantine, so here I'm taking n to be 1, m to be 5, and it's a theorem of Lagrange, and this is defining the set at z at least 0. I mean, obviously, you have to be non-negative to have a solution, but Lagrange tells you that every non-negative integer is a sum of four squares. So that's a Diophantine definition. Once you can define this, you can clearly see that the order relations in the integer is a Diophantine relation. So, for example, you can define the set of known squares in Z. So M in Z, let's say M in Z, such that the complement of the set of squares is clearly Diophantine, and the set of non-squares is also Diophantine because you can define it in a Diophantine way, in such a way, you ask, there exists n such that n squared smaller than m, smaller than n plus 1 squared. And then you apply the previous step that defines an order relation in a Diophantine way. So now the order relation has been made Diophantine, so you can invoke it in your formulas without specifying variables every time. So implicitly, I'm using at least 10 variables for both this and this. All right, so maybe I should have used, okay. Okay, so let me, these are two examples. Let me now tell you a little bit the strategy of the proof of the Matiyasevich Robinson Davis Putnam theorem. So let me actually tell you first the hardest step of the proof. So the hardest step of the proof is very elementary, and is the following: it's to prove that k a to the k, a in z, k in this one, let's say, inside z cubed is Diophantine. So said in informal words, this is saying that the graph, even in a family sense, the graph of the exponential function is Diophantine. So that's, even if you fix one parameter, which is a consequence, let's say a is 2, you're saying that the set of points n2 to the n is a Diophantine subset of z squared. So that is a very strange statement, because you would expect one coordinate to grow polynomial in another coordinate, but somehow if you take enough variables, you are able to construct a family of equations in such a way that the second coordinate grows exponentially with the first coordinate. So once you have that this set is Diophantine, what follows from here is that lots of sets are Diophantine. More precisely, lots of functions are Diophantine. And for those of you that are more familiar with logic, essentially what you can prove from here is that any recursive function is Diophantine. So once you have this, the high-level strategy of the proof is that you are able to encode the set of all Diophantine sets in a Diophantine way. So you can encode Dn, where n is in Z at least 0. These are all Diophantine sets. Remember, there are countably many Diophantine sets in Z because there are countably many polynomials in infinitely many variables subset. In such a way that there exists a polynomial P, maybe a very complicated polynomial, in a certain number of variables with the property that P and X bar as a Z point if X is in the N. This looks a bit complicated, but what this is saying is that you can encode all Diophantine, you can enumerate the Diophantine sets in a Diophantine way. So the belonging of X in D to the N can be read by this family of polynomials. And yes. Yeah. I would say something about that. Yeah, because that, I want to say then why that step doesn't work for other fields. And yes, I can already spoil a bit that uses very clever, uses 4 nested Pell equations, where somehow one parameter of the Pell equation is a solution in another Pell equation in a very clever way, in such a way that you can essentially write down the equation m equal n to the k, which is an illegal operation because n to the k is not a polynomial. But by somehow using properties of Pell equation, you can prove that m and n to the k are congruent modulo something that is bigger than both of them, and then they're equal. So that's Pell equations is the key word, but I will say a little more. Then any recursive function? Yeah, the graph of any recursive function is Diophantine. So essentially, okay, yeah, maybe this is a good step where to say something simple-minded about the history, because this is, the history was, the first way the proof was written was more complicated than this, but essentially this was done by Matiyasevich, the hardest step. And the reduction to all the rest, which is this brilliant idea here of writing the Diophantine way in a Diophantine sets in a Diophantine manner, was done by all the other 3 authors with several contributions. First Robinson independently, and then Davis and Putnam sort of joined there in some sense. But yes, so that's roughly the history. Maybe let me say how then you conclude. Now, if Hilbert 10 had positive answers, even for this family of equations, so this is at positive answers, then you get the contradiction. And here you use these lots of sets are Diophantine, that the set of n such that n is not in Dn would be of the form di for some I. And this is the usual counter-diagonal argument that this is never possible. Whenever you write an enumerable set, the set of elements that do not belong to their index set, so this is a contradiction. This is counter, impossible by counter. This has nothing to do with the n being Diophantine. This is never possible. So, but the fact that Hilbert 10 having positive answers means that comes from the fact that you have proved that so many things are Diophantine that the algorithm that decides this essentially is forcing this thing to be not just recursive, but Diophantine itself. And then you, by the diagonal argument, you get a contradiction. So yeah, to get to Jake's question, okay, what is the proof of the hardest step? The proof of the hardest step uses properties of Pell equation. So proof of hardest step. There are many proofs, but most of them proof of hardest step. More precisely, uses divisibility property. Divisibility property. Properties of Pell equations, of solutions of Pell equations. To Pell equations that are equations of the form x squared is dy squared, where d is positive, square free, let's say, equal or non-square equal 1. D is an integer here. So these are things studied since Euler, very well understood since Euler, and in particular, you study them for this. In the proof, you use this special choice of the a squared minus 1, where the fundamental is very well understood. So the divisibility properties that you use are various, but perhaps the most remarkable one due to Matiyasevich, that he had the insight that this property is important, is that if you impose that a Fibonacci number squared divides another Fibonacci, then you can get a divisibility relation between the first Fibonacci and the index of the other. So in this way, in an algebraic manner, you can access the exponent. And Fn is a solution for the family a squared minus 1, where a is equal to, sorry, a squared plus 1, where a is equal to 2. It's a similar family, and Fibonacci numbers, you can view them as first coordinates of families of Pell equations. So in the original paper of Matiyasevich, he used this. Yes, yes. This was in the original paper of Matiyasevich, but works completely in general. It's a completely elementary property. It's a trivial property, but the insight that this property gives you access to the exponent in an algebraic way was due to Matiyasevich. This was a really, really brilliant step. So, yeah, what about these finitely generated rings? The problem is that, yeah, the same proof simply as a limit. So the limit of this approach, which was understood by the Neff, extended this to the furthest possible extent to zk, and this is the ring of integers of k for k totally real. There is no known way to fix this proof with Pell equations in general. And right after this work of the Neff and Lipschitz extended it to ZL, where L is a quadratic extension of totally real K. So just one step after real K. And this inspired a few years later Putnam and Schlappentock to substitute Pell equations with elliptic curves. And this will be the main theme of this talk. So Schlappentock and independently Putnam, and now Schlappentock, Putnam is written that Putnam independently obtained the same result, and Putnam had all kinds of other criterions using elliptic curves, but this turns out to be the one that was used the most. For what I'm going to talk about in a bit is an analog of this, L over K quadratic. She proved that if L over K is a quadratic extension of number fields, so number field just means here a field that is a finite extension of the rational numbers. Quadratic just means that L is K root something. And you can find E over K an elliptic curve. So remember at the beginning of this talk, I made examples of these homogeneous equations of degree D. And I said for these 3 and 4, that's an elliptic curve. And that's what I mean. So Today we will talk mostly about equations of this form, let's say with f cubic and non-singular, discriminant of f different from 0. Then the solution set here is always a group. And it's a classical theorem in number theory that this group might be not finite, but is always finitely generated. There is always a finite list of elements that you can express all the other elements through that. So there is a well-defined rank that is a finite number, such that the rank of EL is equal to the rank of EK. It's positive. Then OK as a subset of OL is Diophantine. So that's the conclusion. And it is somewhat an extension of this. So essentially what Denef and Lipschitz use here are the unit groups of OK and OL. And this idea was, the idea of Schlappentock was to replace the unit group with a more flexible object, which is an elliptic curve that allows you to define in a Diophantine way a subring over a bigger ring. So you can imagine that this is very useful to try to approach the following conjecture, which is all you need to know, all you need to do to conclude the proof that Hilbert 10 would be unsolvable over OK. And this is a conjecture of both of them, Denef and Lipschitz, which states that Z, for all number fields K, Z inside OK is Diophantine. And the problem is the existence of this elliptic curve. So you can imagine, and that's I will explain it to you, that if you are able to construct such an elliptic curve, well, at least you are moving one step down. So it's not completely inconceivable, though it's not clear, that that gives you a way to go step by step down to Q. And that's actually possible. The main problem is that it is conditional on the existence of such an elliptic curve. And this conjecture, by the way, implies immediately that H10 over OK is undecidable. So if you solve this problem, if you just define Z inside OK, then you are reduced immediately to the case of Z, because you can use the family of polynomial of Matiyasevich, and you have a Diophantine way to recognize that one of your variables is actually integral. And then you add these equations, and then you know first that your variable is integral, all your variables are integral, and then if you had an algorithm over OK, you would have an algorithm over Z, but you have no algorithm over Z, and then you're done. So clearly this is all you need to do. But the existence of the curve is the enemy now, is the thing to be understood. So now it might seem more natural why the following 2009 result of Mazur and Rubin saying that if you assume BSD, then Hilbert 10 over R is undecidable for all R commutative, infinite, and finitely generated over Z. So in particular, all ring of integers of number fields. And let me say that that's actually the real, the only case that at this point was left to be understood. Positive characteristic ring were understood by a bunch of people using completely unrelated methods. And Eisentrager had a very nice way to reduce a general finitely generated ring to a number field. So to a ring of integer or a number field. So this was the real final step. And Mazur and Rubin, okay, say assume BSD. This is the Birch-Swinnerton-Dyer conjecture. It's still open, and it's a Millenium price problem. And so the problem remained open for a bit. And last December, Peter Koymans and myself proved the same without BSD. So H10 is undecidable for all finitely generated infinite rings R. And theorem 2 is, let me call this conjecture 1, though there won't be conjecture 2. Conjecture 1 holds. And as explained, that's enough. So we prove that Z is Diophantine over OK for every number field, the ring of integers of the number field. And theorem 3 is that this is not quite true for every L over K, but for sufficiently many that like we're not yet able to prove it for every L over K, the statement that there exists such an elliptic curve, but we prove it for enough good extension. So for any special quadratic extension, I will tell you what that means. L over K, there exists E over K elliptic curve such that the rank is positive and stays the same. Okay, so the rest of the talk I want to focus on the proof of theorem 3. So I will just, and if there are questions, I can answer more about this, but I already sketched a little bit the idea that theorem 3 implies theorem 2. And the idea is essentially a procedure to go down from L to Q. So it is not quite, you might wonder what happens if L over Q is of odd degree, then there are no subquadratic extension. The thing is that you can always enlarge enough your number field. Maybe let me very, very briefly, maybe I can use here. Maybe let me keep this here. Let me just give you a very brief sketch of the proof of why theorem 3 suffices, at least the idea. So suppose that you want to prove that the ring of integers, the usual integers, are Diophantine over ZF, then I still didn't tell you what special means, and I will tell you in a second. ZL, so L over K is special, and that's really a proof thing. It's not something should be there, but at the moment with the strategy we built, we can prove it only in this case. L over K special simply if L over Q is Galois. L contains Qi root 5, root 7, root 11, 10, 17, root 19. And K, there exists an embedding of L in the complex numbers in such a way that K is the inverse image of the real numbers. So K is in some sense a real subfield of L for some embedding of L in the complex number. So these are not quite any quadratic extension, but they are sufficiently many that you can prove the theorem. So L is necessary K of I in this case. And the idea is that you start with any F, you enlarge it to an L, where you choose L to contain all these things, and you put here L to be the normal closure of F times this all these square roots that are here. And then you have this L, and then you can take any embedding of L in the complex numbers, and you can take the inverse image of the real numbers, and since L contains I, that will be a quadratic extension. Now you apply Schlapentock theorem, and you know that this is Diophantine over this. But you know this for every embedding in the real numbers. So then you can intersect all these embeddings, and you go down to something that is totally real. And then here you have the NF result. So you know that Z is Diophantine here. You have, through the elliptic curves, you know that this is Diophantine here. So this is transitive, and you know that Z is Diophantine here. And now the fact that is Diophantine here forces Z to be Diophantine here. And then you're done. So that's why theorem 3 is sufficient. And for the rest of the talk, I really want to focus on how do you build the elliptic curves. And you might think that this is indeed something really stupid, that one should be able to force a point and should be also able to force that there are no points in a quadratic extension. But somehow our knowledge of elliptic curves on how to control that there are no other points is so that we have a limitation in making true both things at the same time. And this is what I want to talk about now. So you have this rank of the elliptic curve, and you have to prove that it's both positive and doesn't change. So let me rewrite this equation a little bit differently in a way that resembles the first equation. So L here is really k square root of -1. And it follows, you can write the difference of the two ranks and the k. You can write it as the rank of another equation over k. So let me explain what that equation is. For alpha in k non-zero, and if you have E to be given by y square is f of x, where f is a cubic, then E alpha is called the quadratic twist, is the curve simply given by almost the same equation, but you place an alpha in front of y squared. So these equations look basically like the same, and they are not the same over k. That's the point. They are very different over k because you cannot absorb this variable inside of y because you have to take the square root of alpha. So the k solutions might be completely unrelated as you multiply by alpha. And this is a thing that is sort of a very hot topic of study, how the rank of these elliptic curves change in quadratic twist families. But here I'm saying really the twist by -1. So this is almost the same equation. It's minus y squared is f of x. And this decomposition of ranks is an exercise in abstract algebra. It's the fact that if you have an involution of on a vector space of characteristic 0, you can always decompose the vector space as the plus part and the minus part. This is the minus part. And here the involution is the Galois group, the generator of the Galois group of L over K. So these formulas for the rank is an exercise, and it follows that what we want is an elliptic curve such that we want to find E over K such that the rank of EK is positive and the rank of the companion curve is 0. And now both ranks are over K. That's the advantage. I rewrote my condition with a condition on two things with arithmetic on the same fields. Okay, so why is this a tricky problem? Well, let's focus on the second one. So which method do we have to make sure that the rank is bounded, say is 0? An ancient method for this is descent, and is due to Fermat in the first example, perhaps, and was built by many other people. And it is an approximation of the rational point from above, so of an elliptic curve. So you have two descent. Is a special case of descent. So you have this group E minus K. Let's say you want to prove that this group has rank equal to 0. Then at least modulo 2, you can always embed this group in something much more explicit, which I will not define. I would have to spend the rest of the talk to do that. But it's called the 2-Selmer group. And this is, in case K is Q, is a subgroup of the group of square free numbers in Q. So the numbers in Q modulo squared. So it's something very explicit and more amenable to computations. But it's an approximation from above. So a basic strategy to force, here we have two conditions to force the second condition. So might simply be make sure that dimension of this Selmer group, of this 2-Selmer group, is as small as possible, and it turns out that in this case is 2. And I'm already specializing my elliptic curves E. They will be all looked inside this type of curve where the polynomial f of x splits completely inside of K. That's not the only possibility. So the AI here are all in K. But it makes our life significantly easier. And actually, it's really crucial to what I will do in the end. So this two-Selmer group, because of these assumptions, for reasons that I will not explain, is always at least two-dimensional. And if you can prove that it's exactly two-dimensional, you can prove that this is the rank of this is 0. So that takes into account double star. But what about star? So how do you know that the original curve has actually point? That's the step where BSD comes into play. So sort of very simply, in a simplistic way, what Mazur and Rubin did essentially was to study quadratic. That's one possibility. They did it more in general, but here is one case where you can make this work, is that you consider the family of all quadratic twists of a given elliptic curve, dy square is f of x, where d varies. And what you can make sure of is that the two-Selmer group of this object, you can enforce this equation here. And at the same time, you can enforce that two-Selmer of E over K, E d over K, this equation with minus d now, minus d everywhere. So they study now E minus E d. So the companion curve is E minus d. You can make sure that this has odd cardinality, odd dimension, sorry. The dimension of that is odd, and under BSD, that's strong enough. So no, it's a Tate-Shafarevich, just the finiteness of the Tate-Shafarevich groups. If you have control on two-Selmer of this one, you know that is 0, and that will imply without BSD that the rank of that is 0. But if you know that this thing is, let's say, 3-dimensional, then you will know that there is at least a point. But the problem without BSD is, so this is Mazur Rubin. So Mazur Rubin. So what is happening here is, and let me say why they can do this, is that in this family of elliptic curves, you can study very explicitly two-Selmer. So Selmer 2 of E d over K is a space determined by the prime factors by the assignment of symbols pi on pj, where pi on pj is the Legendre symbol and pi on pj are prime factors. Pj are prime factors, so are different from j, prime factors of d. That's at least over q. And over a number field, this is more complicated to make sense of this, but there is a similar statement that once you factor this d into prime elements, then if you know the assignment of all Legendre symbols through a complicated procedure, you can decide through a matrix associated to this assignment, you can decide what is this two-Selmer. So for instance, if you make this matrix as invertible as possible, then you can say that this is maybe 3-dimensional, and then you will know that the rank of that thing is 1 under BSD. But without BSD, you don't know that there is a solution. So you know that this approximation is good, but there is no guarantee that there is a solution. So the idea here is that if overall the approximation step is fine, so this is sort of fine, and this is still mysterious if you don't assume BSD. You have no control on the rational point. So our idea is to revert the situation and start with the situation where the rational points are comfortable, but you obscure the descent process. So the idea is to consider instead the family Fn over d times y squared is equal to f of x, where n and d are your favorite numbers in the ring of integers. Let's say n and d are non-zero in OK. So it's a new quadratic twist family, and it has the property that by construction, the point n over d, comma 1 is in the solution set. So now you have made sure that your elliptic curve has a chance to have a positive rank. And in fact, there is a finite set S. There is S finite inside of K finite, such that is enough that Fn over D is not of the form S times lambda square for lambda in K and S in S to imply that the point n over d, comma 1 is non-torsion. So most of the specialization are actually creating a point, a tautological point on the curve, which is non-torsion. So there are only finitely many bad specializations up to squares that create a torsion point. So you have basically made sure now that condition star is satisfied, but now you have to go back here and you have to run again this procedure of checking the matrix of prime of Legendre symbols. So you made now the existence of rational point sort of very clear, but you have obscured back your two descents. So let me rewrite the curve in a homogeneous form. So we have to do two descent on Fn over d. I can multiply by d to the 4, absorb it in one of the variables, and you can write it in an homogeneous form like this. 3 squared is f of x, where f is x minus a1, x minus a2, x minus a3. Okay, so what do I have to do to run this procedure? Now I have to take this value of d. So let me call it capital F n comma d, which is this binary split quartic form. F n d y squared is f of x. And I have to take the prime factors of this, 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 and this. So I have to take the prime factor of this 4 composing factors of the form, and I have to take the matrix of symbols. And yeah, that's very unclear now, because you need to have control of the prime factorizations of this thing, and you have to know also the mutual Legendre symbols. So suppose that this has 1 million prime factors, maybe you have to know all the reciprocal, the Legendre matrix, the matrix of Legendre symbols of all the mutual prime factors. So God knows how that looks like, but there is an opportunity, which is the case where each of these are actually already primes. Then you know actually almost everything, except some of these assigned. That is this special condition on the number on the extension. So the final idea is to take advantage of additive combinatorics. And the idea here now is make sure that force d n minus dA1, n minus dA2, n minus dA3 to be, let me write almost prime. And I will say in a second what I mean. I will actually make sure that this is prime, this is prime, this is prime, and this is a prime times something which you choose at the beginning of the proof, only in terms of E. So kappa is kappa of the original curve before you start twisting. E is the curve y squared is f of x, which you are twisting in this tautological way to create points. Remember, this is the twist we are looking at. F of x. In terms of E, there is a number kappa which you put inside of D. And this number kappa is made sure to make a little bit of space in your matrix. Now your matrix will not be just formed well, 8 by 8. This is double the number of prime factors, but it will be, yeah, 4 plus the number of primes in kappa times 2 squared. So that's the size of the matrix. So it makes sure to create an original favorable corner of this matrix to make sure that the final 4 primes bring down the rank of this thing to 0. So you make this explicit matrix as invertible as you can, and double star now is forced, and star is forced by default, by design. So you sort of inverted your situation where you made your descent procedure hard, but then I didn't say how you force this, and this is over Q, this would be green tau, but the version, there is a recent version done by Kai just 1 year before for number fields. Actually, with quite some flexibility on the region where you choose N and D. Yeah, so Kai extended the work of Green and Tau over any number field with giving an asymptotic formula actually for the number of choices N and D. As soon as you make sure that you can, there are obvious local abstractions. Sometimes you might make always at least one of these divisible by something, but as soon as you make sure that there are no local abstractions, you can specialize in such a way that this is prime, this is prime, this is prime, and this is a fixed multiple of a prime. And then you have control over to descent, and you make sure by design that the rank is positive. And that's it.
Question, but a short anecdote. In 2012, Matiyasevich was working on the Riemann hypothesis, and the team. But many years before that, during the Soviet period, when it was extremely difficult for Soviets to travel, Matiyasevich visited my home. And as a consequence of that, sometime later, I was interrogated by the Royal Canadian Mounted Police. So, sorry for the non-mathematical
that's fine.
interruption.
That's fine.
These sorts of field extensions, do you expect 50% chance of rank 0, 50% rank 1?
Yeah. When you run over these ones or over Fn over D, or sorry, which one?
Just rank, I mean,
When you run over all quadratic twists. Oh yeah, I think you have to be a little bit careful because there are, over some number fields, there are situations where by root number consideration, the rank is always even. But they are completely classified. Dockschitzer has a, I remember reading in a paper of Dockschitzer, somebody else characterized exactly, but as soon as that doesn't happen, then there is a congruence when the rank is odd, and the congruence for the, and within that family, you expect 100% to have smallest possible rank. So with fixed parity is 100%, and the parity is a congruence usually. The parity of the rank is a congruence on the twist.
is the parity of rank much low, but we can die?
Yes, so if you know Birchens, Wiener, and Dyer, you can actually, I think not for any E, but for most E, you can now prove it under BSD with Alex Smith type of results. So you can prove that yes, 100% has the smallest possible rank with that parity. But without BSD, that's true only for rank 0. So for because there's an upper bound for rank 1, you cannot do it without BSD.
If you're convinced you can make this kind of argument work at all number fields?
Yeah, by now it's written in a way that it applies to.
No, go.
Yeah. It is. He has these two very big recent preprints where he has done. He has pushed his method to the sort of most general setup possible, including all number fields. Yes, an interesting question here would be, can you, since we cannot do it with BSD, what you said, can you at least prove without BSD that for every given elliptic curve that has at least one twist of odd rank, can you prove that it has infinitely many twists of rank 1 using this method? We can prove that if K has at least 6 real places. So there are some subtleties I didn't explain in this matrix. So there are some of these symbols which you have no access to. You don't have access to basically P3 on P2. They are the symbol N on D. So if you would have a better green tau with also knowledge of N on D, the Legendre symbol N on D, then you would have access to Pi and Pj. But we found a way to make the Selmer go down by only knowing P1, P2, P3 modulo kappa. And then there is a nasty thing that happens that kappa divides D. So P1, P2, P3 are the same modulo kappa. So then you are almost in trouble, because then to do this, to bring the Selmer down, you would need divisors of kappa to go very differently, modulo P1, modulo P2, modulo P3. And that's the place where we use 6 real embeddings, because the swap in quadratic reciprocity is also governed by the real places. So the fact that they are the same modulo kappa doesn't force a divisor of kappa to be the same modulo them. And then we do a delicate thing with the signs, and we use that there. That's where we use that is a special quadratic extension. We use that there are at least 6 real places. But this is really something stupid of now. I strongly believe that with some extra tricks, you can get rid of it. Oh, yeah, you do. No, you do. That's all in kappa. That's all in kappa. Like the class number, all the original garbage coming from the number field is all taken by kappa. Kappa somehow makes sure that you can work only with principal primes like this. And sort of any class coming from a ramified extensions is already killed by kappa in the process. So kappa kills all the stuff, and computations then look really like Q.
When you answer questions, I guess it's very Italian, but very handling.
Oh, yeah. I hope the paper is not as end-waving. You can have a look and let me know.
In the beginning of your talk, you said that it was a problem was kind of loosely stated. And so what are the future prospects? I mean, after this result, are there still, what are the big questions in this general field?
Oh, yeah. One big problem is Hilbert 10 over Q. And the same approach there would be to try to prove that Z inside of Q is Diophantine. So it's more a question. And there is a nice conjecture of Berry-Mazur that says that if you take a reasonable variety over Q, and you take all Q point, all the rational solution, and you take the topological closure and the real point, then this should have finitely many components. So if these were Diophantine, you would have immediately contradiction with that conjecture. So actually, it's conjecturally expected to be not the case, which makes very unclear how you are approaching this problem if the conjecture is true. But you might first try to see if the conjecture is. Hilbert formulated for Z, but Matiyasevich argues in one of his surveys papers that if Hilbert was told that the answer was negative, he would have immediately asked for Q. Because the Hilbert expected the answer to be positive over Z, which implies positive answer over Q. But then they wanted to know what is over Q. So that's still unknown. Sorry, what? Yeah. Yes. Over Q, it is still expected to be undecidable. But not for this reason, then. At least conjecturally. It's all conjecture. Yes, it is expected that there is a different way to prove that is undecidable without proving that Z is Diophantine, without reducing to the case of Z. So that's the current. Yeah, people don't have any reasonable approach on this problem at the moment. So it's entirely open.
You said something about
Z bar, Rumley with capacity. No, he proved that there is an algorithm to decide solvability over Z bar, or of an equation over Z bar. So I give you an equation, a polynomial over Z bar, and you have to decide whether it has a Z bar point, and Rumley has an algorithm. Like, yeah, the answer is yes.
Do you do any averaging over N and D to control the two similar?
Not really. No, not really. We only impose essentially congruences modulo kappa. But we do use at some point that you have enough. You have the asymptotic. We mildly use that you have the asymptotic formula just to throw out a small number of exceptional N and D. But yes, yeah. But no, we don't need anything more than infinitely, but with some control actually on the size. Yeah, that you can decide.
Yeah, I don't know.